So in this video, I'm going to prove a claim, which is proposition 1.7 in Poland. So before, this claim is about elementary family, and therefore we introduce the definition for elementary family first. So the definition, it has three pieces. The first one is the empty set has to be in E. And the second one, if you have two sets that are in E, the intersection of those two sets is still in E. And the third one is if you have a set that is in E, then the complement of that set can be written as a finite disjoint union of the elements in E. So E is an elementary form. E is an elementary family if and only if it satisfies all of the three conditions. And our claim is that if E is an elementary family, then A, which is a collection of finite disjoint union of numbers in E, is an algebra. So here I want to clarify that the collection A here is, so each element in this collection A is a finite disjoint union of numbers in E. So we're showing our goal is to show this is a sigma, this is an algebra. And recall that whenever we define an algebra or sigma algebra, we need to keep in mind what the universal set is. So here the universal set is X. I forgot to mention that when we define the elementary family here, we're actually saying that the context is elementary family of set X. So here X is our universal set, and we want to prove that if E is an elementary family, then this collection A is an algebra of set X. Okay. So the first, let's just follow the definition, right? Let's first prove that the empty set is in A. Why is it true? It is true trivially, right? Because any set contains empty set. And the second thing is, well, you can also think about the empty set is in A because the empty set is a member of E, and E, and one element in a number of E is of course a finite disjoint union, right? Because it's just itself, so therefore it is in A. And the second one is X is in A. Again, since we want to show that X is actually a member of E, and let me think about how to show that. Okay, so X is a member of A because so here we'll give a short proof. Since the empty set is in A, the empty set empty is equal to X, and so X, and we recall the definitions here, right? So X is a finite disjoint union of elements in E, and this is precisely the definition of elements in A. So X is in A. And then the third one is what is the third one? It is closed under countable union. So what I'm gonna argue is that it suffices to show that if is suffice to show given A1 dot 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 to AN that is in E, then the union of I is equal to 1 to N of AI is in E. Or is in A. So why that is sufficient to prove that? So because if say like let's say we have a collection of elements in A, and each of the element is going to be in terms of finite disjoint union of elements in E, right? So when you, since we're showing that it is closed and countable union, oh sorry, it's closed and finite union because we're trying to prove it's algebra. Sorry. So we have this finite, right? Okay. And then because our goal is to show it is closed under finite union and each element is finite union. So at the end, you are actually showing a finite disjoint union of elements in E is in A. So I hope that is clear. So in short, my claim here is that to show that given a countable element, given a finite element in A, to show the finite disjoint union of those elements is still in A is equivalent, or it suffices to just show that assume I have some elements in E and to show the finite joint union of those elements in E belongs to A. Okay, so that's what we're going to show. And we're going to show by induction. So suppose A, B are in E, right? And then we want to show first is let's do A2. Let's do A1 and A2. So we want to show that A1 union A2 is in A. Okay, and how do we show that? Recall everything in A should be in terms of finite disjoint unions, right? Here, I'm not sure because A is an element in E and A1, A2 are both elements in E, and the union of them, I don't know if they are, if it is a union of finite disjoint elements, right? It is certainly finite because there's two elements, right? But I'm not sure if they are disjoint, and they're in E, right? But I'm not sure if they're disjoint, like because we're not assuming they're disjoint. All we assume is A1, A2 are in E. So how to get rid of how to show that A1 union A2 is in A? We recall the definition for elementary family. Actually, there is a hint here. Remember that if a set is in E, then that means the complement is a finite disjoint union of elements in E. So that kind of like inspires us if we can actually write this in terms of using the advantage of the definition for elementary family that the complement is some sort of finite disjointing. So that is the intuition. So my first try would be try to write A1 union A2 in terms of in terms of some disjoint union of sets in E. Well, how about this? So A1 set minus A, so A1 union A2 is equal to, so if you draw those two circles, this is A1, this is A2. What we can do is we can do, so the shaded part is A1 set minus A2, and then the shaded part here is A2, and those two sets are disjoint, right? So this is equal to A1 set minus A2 union A2, and then we know that A2 is, so we made sure that this is this joint union, right? So what we had before is we have A1, A2 is in E, and but we're not sure if the union is a disjoint union. But right now we disjointify the union, so we have disjoint, but we are not sure if we if this A1 set minus A2 is still in E or not. So this is what we need to check. So is this true that this is in E? So we know for sure this is in E because by the assumption A2 is in E. Okay, let's so show this is in E. So recall that A1 set minus A2 is equal to A1 intersect A2 complement, right? Okay, and then we know that A2 complement is actually equal to disjoint, can be written as union of finite disjoint sets. So let's do A2 complement is equal to J is equal to 1 to N of Cj, where Cj is in. Okay, so we have A1 intercept. Okay, and then by the distribution law of the sets, we have the union J is equal to 1 to N, A1, AI, AJ intersect C, A1, sorry, A1 intersect CJ. So we have this, right? Okay, so what do we have here? They are disjoint for sure because CJs are disjoint. And since A1 CJs are in E, A1 intersects CJ is in E. So therefore, this is a collection is of E, and they are disjoint. So therefore, it is indeed in E. And so hence A1 union A2 is in A, right? So we finished the base case, and now let's try to finish the induction step. So suppose A1 union dot 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 union AN is A, show A1 union to AN plus 1 is in A. So what are we trying to do? Well, in order to show that, notice that using a similar trick, right? We disjointify that. So we have A1 union, AN set minus AN plus 1, okay? And the union AN plus 1. Okay. So this is equal to, right. Okay, and let's try to show this. So I'm wondering if I should just use, so this is a disjoint sets, right? So, and we know this is in E, and I just need to show this is in E. And then the question is how to show this is in E. Okay, so we have A1 union AN intersect AN plus 1C, right? So we have this. Okay, and so this is, again, this one can be written as disjoint, finite disjoint union. So we can write this as I is equal to 1 to about di. Okay, where di is in E, right? So what we have is we have A1 intersect this union A intersections, and then union AN plus 1. And let's see, what is this, right? This is equal to A1. This is equal to the union I is equal to 1 to N A1 intersect DI. Union dot 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 union. So everything will be exactly the same. AN union AN plus 1. Okay. And then again, this is in E, and this is in E, and therefore, this is in A, this is in A, and so actually we don't, the observation is fine. Sorry, I think my Apple Pencil just died. So it's good that we have this observation, but we actually don't need it. So the point is that this is a finite disjoint union of elements in E. This is, and this is a finite disjoint union. And this is also an element in E, and those unions are disjoint. Therefore, it is in A, and therefore we're done. Okay, and then the next is show closed under complements. So suppose so I'm gonna suppose an element in A, and I want to show that the complement of this element is also in A. So let A1 AN in E, and we and because this and let them to be disjoint. Okay, so J is equal to 1 to N of AJ. Certainly it is in A because first of all, each element is in E, and this is I set them to be disjoint. So the union of them is also in. So the union of them is in is an element in A, and we want to show that the complement of this is also in A. Okay, how to show that? So notice that if you want to show the complement of A, right? This is equal to intersection J is equal to 1 to N of AJC. So this is equivalent as this. Okay. And what about this? So we know since AJ, J is equal to 1 to N, are in E, A complement J is union of I is equal to 1 to J of C I of B I J. Okay, and then we can put them here. So it's intersection A of the union I is equal to 1 and then J of B J I. Okay, so this is just equal to the union of B, the union of B1 intersect intersect B J. Or let me think about this. Union of so to align with the notation with the book, I'm going to switch this to here, this to here. So IJ. So I goes to the index with the I goes to the index that let me think about this. J is from 1 to N. Okay, sorry. So to align with the textbook, I think I was correct at the beginning. So where intersection J is from 1 to N and in J, okay, so it's going to be 1 to N and okay, so this is going to be J1 to J to JJ. So where J will be ranged from 1 to N, which is here, and J so the reason that I'm doing like J1 to JJ so is because I'm trying to take care of this. Okay, so right, so it's better to use a different notation actually, as I kind of see why the book use uh a different notation than J. Okay, so I have to so let's stick with my notation. So we have J that is from 1 to n, which is taking care of this, right? And notice this. So there are I is equal to 1 to I is equal to J. Um, so if I denote each of the I above here, instead of writing I, because I want to write them explicitly, I cannot write I. So each of them is actually I. So this is I, where I ranges from 1 to JJ. That's what I'm doing. I just want to write them explicitly, and that may be, and I am kind of lack of the letters to use. So this is going to be JJ is larger or equal than 1, smaller or equal than JJ. Okay. So as you see, as you observe, this because B since B1 J JJ are this actually is J. So since since each element is in E, so by definition, and then there's and so finite intersection is still in E. Therefore, the union, and then this is really finite union. So finite arrangement of all those combinations. Okay. So this is finite union. Okay. Therefore, hence, we call that finite disjoint union of elements in E is belongs to A. Therefore, we have this belongs to A as desired. I do want to mention a little bit about the calculation that I did here. So I was working a little bit ahead before I make the video. So remember distributive law is nothing but distributive law. So if I have a union, right, from AI to AN, intersect one single set B, and this is equal to the union of AI intersect B for each I. This is called distributive law of set. And the question arises naturally is that if would it be no longer an individual set, but another union of sets. So this is kind of equivalent with B here, right? And then I'm wondering what is this? So let's just be patient and write everything clearly. So the step here I'm trying to do is I recognize this as one single element. That's why I use the distributive law and I got this. And inside of this, you can see this is something you're familiar with, right? And you use distributive law again for the inside part, and that gives you this expression. And therefore you have, now you can see that you have I is equal to 1 to J1, and then I is equal to 1 to J2. Actually, I'm not sure if it's a good idea to use I or a different thing. Let me use and here let me use and therefore we have okay. And we have AI intersect and here I have and right here I have this. And as you can see here, it is equal to union, right, of a A1 intersect A2, but I and M can vary, right? So I'm just gonna I and M. So this is equal to so I could be anything between 1 to J1, and M could be anything from 1 to J2. Okay, and if you are still in doubt a little bit, I wrote like a simple version of this. So for example, we have these two sets, right? But this could be very complicated. But what if we just do the simple case just to show our idea what is really going on? So we have this. And again, I treat this as one set, and I use the distributive law on this expression. So I got this expression. And for each individual bracket, I apply the distributive law again. So I obtain this. And as you can see, so this is really a union of the sets, right? So, and what are those sets? Those are sets that are exactly in this form. So we have a union of two elements intersect each other, where the index ranges are possible based on the index here. So this is about you take the so this is about the intersection of the unions of sets, the intersection of the union set. Of course, there's analog result on the union of the intersection. So what if this is instead of union, this is intersection, and then in the middle this is a union. So it's going to be the same, except so at the end, our result is going to be the intersection of any two unions. Okay, so I think it is a little bit complicated technical result, but I think it's good to straight it out. So next time when we see it, we can just use it directly.